Continuing on with the Chapter 1 lecture for Chem 112, we're now going to be discussing the idea of valence bond theory and chemical bonding. This is really critical to understanding bonding at a more fundamental level, and we'll be applying principles from valence bond theory throughout the remaining chapters in organic chemistry. So, what is valence bond theory? Well, valence bond theory is the idea that a chemical bond consists of an electron pair shared between two atoms. And a chemical bond is formed by the overlap of two half-filled atomic orbitals or hybrid orbitals. So for example, if we're describing this single bond between two hydrogen atoms, we have two electrons shared between these hydrogen atoms. This bond is formed via the overlap of two hydrogen 1s orbitals, which are each half-filled atomic orbitals, to yield a bonding molecular orbital. Okay, let's now talk a little bit about the types of bonds. So sigma bonds are involve an overlap of atomic or hybrid orbitals directly between the bonded atoms along the bond axis. So for example, if we look at the bond between these two oxygen atoms, the sigma bond represents often the single bond shared between two atoms. It's the overlap of two atomic or hybrid orbitals directly between the bonded atoms along the bond axis. When you think sigma bond, think single bond. Pi bonds, on the other hand, represent your double and triple bonds. Pi bonds involve the overlap of unhybridized p orbitals perpendicular to the bond axis. So as you see for these two oxygen atoms, we have two p orbitals. They're overlapping perpendicular to the bond axis, and this gives our pi bond. Looking at this oxygen-oxygen bond, we have our sigma bond as one of the bonds formed between the two oxygen atoms. And then we have our pi bond. So we have our pi bond, which constitutes the double bond shared between the two oxygen atoms, and the sigma bond represents the single bond shared between the two oxygen atoms. Putting this together, if we look at our two oxygen atoms, we have our sigma bond, which is the overlap of the two oxygen p orbitals along the bond axis. And then the pi bond is the overlap of p orbitals perpendicular to the bond axis. And these two different types of bonds, these two different types of orbital overlaps, represent this overall oxygen-oxygen double bond. Now, it's really important to note that orbitals are phased, and the phasing amplitude can be positive or negative. This is not charge. This is closer to in physics when you have a wave. There are regions of positive and negative amplitude. Depending on the phasing, this phasing can be either constructive or destructive, bonding or anti-bonding. In order for the overlap of orbitals to form a bond, regions of the same phase must overlap. So we see in this case for our bonding molecular orbital, when we're forming a bond, we're overlapping regions of the same phase. This is why I told you earlier on to shade the p orbitals when you draw them to note the fact that they are phased. It has a region of positive and negative amplitude. And to form a bond, we overlap regions of the same phase. This is known as a bonding molecular orbital. In terms of destructive interference, if we try to overlap regions of the opposite phase, we get what's known as an antibonding molecular orbital. It is important to pay attention to orbital phasing, as that helps us understand how orbitals can overlap to form bonds, both sigma bonds and pi bonds. Okay, we're now going to begin to describe chemical bonding using MO theory, molecular orbital theory. So when orbitals combine constructively, a bonding molecular orbital is formed. So if we take these hydrogen 1s orbitals and overlap them constructively, we get a bonding molecular orbital. When orbitals combine destructively, an antibonding molecular orbital is formed. Notice that in the bonding molecular orbital, we are sharing electron density between our two atoms, while in an antibonding molecular orbital, we are not sharing very much electron density between our two atoms. In fact, there's almost like a node present between our two atoms. The overlap of atomic orbitals or hybrid orbitals yields a bonding molecular orbital and an antibonding molecular orbital. Two orbitals in, we get two orbitals out. We take two atomic or hybrid orbitals, we get out two molecular orbitals. So in this case, when we overlap these hydrogen 1s orbitals, we get a bonding molecular orbital and an antibonding molecular orbital. And as you can see, the bonding orbital is lower in energy. This makes intuitive sense. The same reason why bonding electrons are lower in energy. If we have these electrons and we place them in between two positively charged nuclei, we're sharing electron density between our two atoms, our electrons are going to be lower in energy. That makes sense intuitively. Describing this from an orbital box diagram perspective, each of the hydrogen atoms contributes one electron. Hydrogen has a 1s1 configuration, it has one valence electron. So the hydrogen, which has this one electron in its 1s orbital, will overlap its 1s orbital with another hydrogen atom's 1s orbital. These two orbitals overlap and generate bonding and antibonding molecular orbitals. We take our two electrons, one from each hydrogen atom, and we fill the bonding and antibonding molecular orbitals. As you can see, those two electrons go in the lowest energy bonding molecular orbital first. So what this is saying is that when we take these hydrogen 1s orbitals and overlap them, we get a bonding molecular orbital where we have two electrons shared between our hydrogen atoms. In terms of filling these orbital box diagrams, electrons are placed into molecular orbitals. One moment. Electrons are placed into molecular orbitals, starting with the lowest energy bonding molecular orbital. Now, where things get interesting is when we start to talk a little bit about p orbitals. P orbitals can overlap on the bond axis to give sigma bonds, and that in turn yields a bonding molecular orbital and an antibonding molecular orbital. P orbitals can also overlap parallel to the bond axis to give pi bonds and pi star antibonding molecular orbitals. Notice for the bonding molecular orbital for our pi bond, we're overlapping regions of the same phase, while for the antibonding pi star molecular orbital, we are overlapping regions of opposite phase. Okay, so how can we use this? Well, let's tie what we've learned about molecular orbital theory and valence bond theory to begin to describe hybridization. So, to form a bond, as we discussed, the two orbitals must be half filled, they must have the proper geometry accessible to overlap, and they must be close in energy. Overall, the reason why we form bonds is that we want to minimize electron energy by forming bonds. To accomplish this, to minimize electron energy and to form bonds, atomic orbitals are combined and hybridized to yield hybrid orbitals with the proper geometry and energy for bonding. As is a common theme, the number of atomic orbitals combined is equal to the number of hybrid orbitals produced. In other words, the number of orbitals you put in, be it for bonding or hybridization, is equal to the number of orbitals you get out. So, what does hybridization look like? Well, look at carbon, for example. So, carbon has a 2s orbital and three 2p orbitals. These are the valence orbitals, the outermost orbitals that are most relevant for bonding. It also has a 1s orbital, but that's not really relevant for this discussion. Carbon also has 4 electrons to its name. If we fill in our orbital box diagram without any hybridization, we see that carbon initially has a full 2s orbital, and its 2p orbitals has 2 of them that are half filled. So carbon, unhybridized, has the potential to form 2 bonds. That's not really taking into account the fact that in terms of geometry and in terms of orientation, these 2p orbitals aren't set up really for efficient bonding. So what we're going to do in order to generate hybrid orbitals with the correct energy, occupancy, that meaning that they're half filled, and geometry, we're going to hybridize these 2s and 2p orbitals to generate 4 hybrid orbitals. We took 4 atomic orbitals and we get out 4 hybrid orbitals. These hybrid orbitals, importantly, have the correct geometry, occupancy, and position for efficient bonding. So now, as you can see, looking at the carbon hybrid orbitals, we have 4 half-filled orbitals. These are hybrid orbitals. Ergo, we can form potentially 4 sigma bonds. Now, what's really important during hybridization is that the hybrid orbital has the average energy, position, and orientation of the combined atomic orbitals. And the reason why this is really important is the molecular geometry is determined by the shape of the orbital overlap. how these hybrid orbitals are arranged in three-dimensional space is directly linked to the three-dimensional shape and orientation of our molecule. So for example, if we look at the sp3 hybridization, for example, if we look at the sp3 hybridization, we combine an s orbital and three p orbitals to yield four sp3 hybrid orbitals. And notice how each of the hybrid orbitals has almost like a mathematical average in terms of the position, orientation, and energy of the atomic orbitals that we combine together. Okay, let's talk about the different types of hybridization, and let's talk about the impact in terms of overall geometry. So the sp3 hybridization occurs when you combine a 1s and three p orbitals, four orbitals in total, to yield four sp3 hybrid orbitals of identical energy. We call these orbitals degenerate. Now, examples of atoms with an sp3 hybridization include the central carbon of methane and the central nitrogen atom of ammonia. Atoms with four electron groups, be it bonded atoms or lone pairs, adopt an sp3 hybridization. The sp3 hybridization is associated with a tetrahedral electron pair geometry and a 109.5-degree bond angle. So if we think about the bond angle in methane, this bond angle, the angle separating the carbon-hydrogen bonds, is 109.5 degrees. This is why we draw methane the way that we do. It's to reflect the fact that this bond angle is 109.5 degrees. Okay, let me redraw this for a moment just so it's within the frame of the page. So if we take a look at methane, part of the reason why we draw methane in this way is to reflect this bond angle. And this bond angle is a consequence of the hybridization of our central carbon atom. And again, just to reiterate, part of the reason carbon adopts this sp3 hybridization is to accommodate the fact that in methane, it wants to form 1, 2, 3, 4 sigma bonds, so it needs 4 hybrid orbitals. Let's delve into methane a little bit more. So looking at methane, to form the 4 sigma bonds, the 4 single bonds found in methane, carbon adopts an sp3 hybridization. These sigma bonds are formed via the overlap of a carbon sp3 hybrid orbital and a hydrogen 1s atomic orbital. One thing I'd like you to keep in mind is because we're forming 4 carbon-hydrogen bonds, we are overlapping 4 times a sp3 hybrid orbital and a hydrogen 1s atomic orbital. As a general rule of thumb, the number of half-filled hybrid orbitals indicates the number of sigma bonds the atom can form, in this case 4. 1, 2, 3, 4 half-filled orbitals, we can form 4 sigma bonds. So for example, if we have an sp3 hybrid orbital that's half filled and a hydrogen 1s atomic orbital, we can overlap these orbitals in order to form our sigma bond, and we also get a sigma star orbital. Because we combined 2 electrons, we just have 2 electrons in our bonding molecular orbital. Now, as we discussed in terms of the 3D arrangement of these bonds, because this central carbon atom is sp3, our carbon-hydrogen bond angle is going to be 109.5 degrees. Okay, let's take a look now at the sp2 hybridization. Combining an s orbital and two p orbitals, three orbitals in total, yields three sp2 hybrid orbitals. And importantly, one p orbital is unhybridized and can be used to form pi bonds. So as you can see, when we combine an s orbital and two p orbitals, we end up with three hybrid orbitals. These are sp2 hybrid orbitals. And we have left over an unhybridized p orbital that can be used to form pi bonds. So taking a look at the sp2 hybridization, we combine an s orbital and two p orbitals, and we get out three hybrid orbitals. As a consequence of the fact that we have this leftover unhybridized p orbital, many atoms with the sp2 hybridization can use that leftover half-filled p orbital that's unhybridized to form pi bonds. Generally, atoms with three electron groups, bonded atoms or lone pairs, adopt an sp2 hybridization. This corresponds to a trigonal planar electron pair geometry and a bond angle of 120 degrees between the sp2 hybrid orbitals. One thing to note, sp2 orbitals are shorter and lower in energy than sp3 orbitals because we have more s character and less p character. As you can see, s orbitals are lower in energy. And as such, the more s character we have, the more s orbitals that we're combining together compared to the number of p orbitals we're combining during hybridization means these hybrid orbitals for the sp2 hybridization have more s character, they're lower in energy, and they're shorter. This is going to come into play later on when we talk about bond length and bond strength. So let's do a case study now and look at formaldehyde. So here's what formaldehyde looks like in terms of a Lewis structure. As you can see, looking at this central carbon, there are 1, 2, 3 bonded atoms. So we have 3 electron groups. So this carbon has an sp2 hybridization. To this end, we can also take a look now and just fill in what this would look like for carbon. So carbon has 1, 2, 3, 4 valence electrons. We take these atomic orbitals, hybridize them together, and we get 1, 2, 3 hybrid orbitals. So we can form up to 3 sigma bonds, and we have a half-filled unhybridized p orbital that we can use to form a pi bond. So the 3 sp2 orbitals are used for sigma bonds, and the unhybridized p orbital is used to form a pi bond. For those curious as to what oxygen looks like, we can repeat the same process for oxygen. In this case, we can form the 2 bonds for oxygen using just the p orbitals oxygen has without hybridizing. So, looking at formaldehyde in detail, looking at these CH bonds as we see in our orbital picture, this sigma bond is formed via the overlap of a carbon sp2 hybrid orbital and a hydrogen 1s atomic orbital. Here's what it looks like in box diagram form. We overlap these 2 orbitals, we get a bonding and anti-bonding molecular orbital, and all is good. Now, let's take a look at this double bond as it has 2 major components. The first component is the sigma bond. This sigma bond is formed via the overlap between a carbon sp2 hybrid orbital and an oxygen 2p orbital. As you can see, oxygen has a half-filled p orbital that has the correct geometry and orientation, and it's half-filled, so oxygen can use that p orbital to form the sigma bond, the single bond component. In terms of the pi bond component, carbon has a available half-filled p orbital. Oxygen has an available half-filled p orbital that's perpendicular to the bond axis, and we can overlap these orbitals to form a pi bond between the carbon 2p and oxygen 2p orbital overlap. So let's see what this looks like in terms of box diagram form. So we have the sp2 orbital for carbon. We have the 2p orbitals for oxygen. And let me draw these a little higher. And we have the 2p orbital for carbon. The first orbital overlap generates the sigma bond. The second orbital overlap generates the pi bond. And then we also end up with the sigma star and pi star respectively. Let me draw those with the correct scaling. There we go. So, key thing here, because this carbon has adopted an sp2 hybridization as a half-filled p orbital that it can use to form pi bonds. The sp2 hybridization has an impact on the geometry and the bond angles. And as we've discussed, this bond angle here, because this central carbon is sp2 hybridized, this bond angle is going to be 120 degrees. Okay, let's look at the last major cases of hybridization that we're going to discuss, which is the sp hybridization. Combining an s and p orbital, two orbitals in total, yields two sp hybrid orbitals, and we have left over two p orbitals that are unhybridized and can be used for pi bonds. An example of a molecule containing a carbon with an sp hybridization would be acetylene, which looks something like this. This carbon atom has an sp hybridization, and as you notice, these two unhybridized p orbitals can be used to form 1,2 pi bonds. The second thing I'd like to draw your attention to is that sp orbitals, because they have a large amount of s character, are the shortest and lowest energy hybrid orbital. They have more s character and less p character. Now, how does this hybridization impact geometry? Atoms with two electron groups, be it bonded atoms or lone pairs, adopt an sp hybridization. This corresponds to a linear electron pair geometry and 180-degree bond angles. So if we have a carbon that's sp hybridized, we'd be looking at a bond angle of 180 degrees. Let's unpack the sp hybridization a little bit more with a case study. This time we're going to be looking at acetylene, C2H2. So in order to form the two sigma bonds and two pi bonds at acetylene, carbon adopts an sp hybridization. Two of the sp orbitals are used for sigma bonds, and the two unhybridized p orbitals are used to form the two pi bonds. Again, carbon has 1, 2, 3, 4 valence electrons. We hybridize our s and p orbitals together to make two hybrid orbitals, and we have remaining two unhybridized p orbitals that can be used and overlapped to form pi bonds. Now, each of these carbon atoms in acetylene, because there are 1, 2 bonded atoms, 2 electron groups, these two carbons are both sp hybridized. Let's show the orbital overlaps that form this triple bond. So for carbon, we have the sp hybrid orbitals, one each. These hybrid orbitals can overlap to form the sigma bond and the sigma star antibonding molecular orbitals, respectively. So this is the first single bond connecting our two carbon atoms. Let's now look at the half-filled p orbitals. In this case, each carbon atom has two half-filled p orbitals that it can overlap to form two pi bonds. Additionally, we end up making some pi star antibonding molecular orbitals as well, but those are much less important. The key thing I want you to take away from this is that we're able to form a single bond between the two carbon atoms, and then the double and triple bond is formed via the overlap of these unhybridized p orbitals. So looking at this orbital diagram, the sigma bond is formed via the overlap of the two carbon sp hybrid orbitals, while the pi bonds are formed via the overlap of the carbon 2p orbitals, perpendicular to the bond axis. Importantly, because these carbons are sp hybridized, we have a bond angle of 180 degrees. The reason why it's very important to get a sense of what orbitals are overlapping to form a specific bond is that impacts the bond length, the bond strength, and how that bond is going to behave in certain chemical reactions. So, we've talked about the different types of hybridization and the impact on a molecule's shape in terms of bond angle and geometry. Let's now talk a little bit about the impact of lone pairs during hybridization. When you look at the hybridization for a given atom, suppose we're looking at nitrogen, which is a 5a element, and it has 5 valence electrons. The number of completely full hybrid orbitals indicates the number of lone pairs on the central atom. So in this case, when we take nitrogen and we combine the s and p orbitals together to make sp3 hybrid orbitals, we notice this time we have 3 half-filled hybrid orbitals and 1 full hybrid orbital. This full hybrid orbital represents a lone pair being held in that hybrid orbital. So for example, for nitrogen, when it hybridizes to the sp3 hybridization, one of those hybrid orbitals is just already full with a lone pair and can't be used for bonding. So nitrogen in an sp3 hybridization, it's capable of forming 3 sigma bonds and using one of its hybrid orbitals just to hold a lone pair. So we have three half-filled sp3 hybrid orbitals, while one sp3 orbital contains a lone pair for nitrogen. Importantly, the energy of an electron lone pair depends on the orbital that the lone pair is located. As we discussed, orbital energy decreases with increasing effective nuclear charge and increasing electronegativity. For example, if we compare nitrogen and carbon, because nitrogen is more electronegative, if we compare the energy of our given atomic orbitals and any hybrid orbitals that we make from those atomic orbitals, we see that nitrogen, the electrons found in the nitrogen orbitals are lower in energy. We can also take this further. The given hybridization of our hybrid orbital directly impacts the energy of an electron placed in that orbital. Generally, the more s character, the lower energy orbital you have, with sp hybrid orbitals being the lowest in energy, sp3 hybrid orbitals being the highest in energy. Now, why is this important? Well, because orbital energy affects lone pair energy, we need to know how to identify hybridization and identify what orbital the lone pair is located in for us to understand its energy and thus its reactivity. So again, you need to consider what atom are we dealing with? More electronegative atoms have lower orbital energies. And what is the hybridization? The sp hybridization, those hybrid orbitals are lowest in energy. sp3 hybrid orbitals are the highest in energy. Okay, so let's apply this to an example. So here we're asked, what is the hybridization of nitrogen in CH2NH? So first, we're going to need to generate a Lewis structure. So let's do just that. Let's take our systematic approach and count our valence electrons. So carbon, we have 4 electrons. Hydrogen, we have 1 electron times 3, which gives us 3 electrons. And nitrogen, we have 5 electrons. So we have 12 electrons to work with. Carbon and nitrogen are going to be our central atoms. We'll surround the carbon with 2 hydrogens, the nitrogen with a single hydrogen atom. We will form 1 bond each. That uses up 2, 4, 6, 8 electrons, giving us 4 electrons remaining. From here, we'll add lone pair electrons to each atom until we complete the octet. We've burned through all of our electrons. Nitrogen is happy. Carbon is missing 2 electrons. So we're going to take one of our lone pairs and we're going to form a double bond. Okay, now that we have this structure prepared, let's take a look at this nitrogen atom and let's take a look at its hybridization. So in this case, we have 2 bonded atoms. One, 2, plus 1 lone pair. So we have a total of 3 groups, 3 electron groups surrounding nitrogen. And to accommodate that, nitrogen needs to adopt an sp2 hybridization. We can also see this if we think about this from an orbital box diagram perspective. If we need to form 2 sigma bonds and we need to hold a lone pair and we need to form a pi bond, so let's just make a note of that. So we have one lone pair, one pi bond, and two sigma bonds. To hold this lone pair and to form the two sigma bonds, we need to adopt an sp2 hybridization. That in turn gives us three hybrid orbitals and a p orbital. Now, why am I going through the effort of drawing this? Well, we can see our lone pair is accounted for, our pi bond is accounted for, and our two sigma bonds are accounted for. So this nitrogen is sp2. Now, if we compare the lone pair in this molecule to that of ammonia, where this nitrogen is sp3, and this lone pair, as we discussed, is held in an sp3 hybrid orbital. Considering that if we looked at the sp3 hybrid orbital, the sp3 hybrid orbital is generally higher in energy. It has less s character. So if we compare these two lone pairs, and we compare a lone pair in an sp2 orbital versus a lone pair in an sp3 orbital, we can see very clearly which one is lowest in energy. The lone pair in sp2 orbital is lower in energy. Now, do you need to draw the full orbital box diagram? Not necessarily in this case. You could say this nitrogen's sp2, this nitrogen's sp3. sp2 orbitals are lower in energy, so the lone pair in an sp2 orbital is going to be lower in energy. That's why the lone pair on the nitrogen in this molecule is lower in energy compared to the lone pair on the nitrogen in ammonia. Hybridization has an impact on lone pair energy. Very important for the next chapter. Okay, so let's talk a little bit and let's do some examples of molecular orbital theory practice. So here we're going to be doing some case studies and we're going to be drawing out some orbital diagrams. So we're asked to draw an orbital diagram for hydrogen cyanide, and we're asked to clearly indicate the hybridization of each atom and the orbitals used to form each bond. So I'd want you to pause here at this time and work on drawing the orbital diagram for HCN, and then we'll discuss this example momentarily. So let's start from scratch here. The first thing that I like to do is before I make an orbital diagram, I want to draw a basic Lewis structure. So in counting out the valence electrons, hydrogen has 1 electron, carbon has 4 valence electrons, and nitrogen has 5 valence electrons. So we have 10 electrons to work with. We're going to put carbon as our central atom and surround it with hydrogen and nitrogen. We'll form one bond each, giving us 6 electrons remaining, and then we're going to add our lone pair electrons. We've ran out of electrons. Carbon, terribly unhappy, only has 4 electrons. Let's take a lone pair and form a double bond. Carbon, still unhappy. It only has 6 electrons. It wants 8. We're going to take another lone pair and convert it this time to a triple bond. Okay. Looking at this carbon atom, we see it has 2 sigma bonds and 2 pi bonds. You can also say it has 2 bonded atoms. Both of these pieces of data tell us that this carbon is sp hybridized. Likewise, this nitrogen has 2 pi bonds, 1 sigma bond, and 1 lone pair. This tells us, because this nitrogen has 2 bonded atoms or lone pairs, that this nitrogen is also sp hybridized. Okay, now that we've identified the hybridization of each of our atoms, we can now go about constructing an orbital diagram. So first, let's look at what orbitals we have available to overlap. This hydrogen has a 1s orbital and it has one electron in it. Carbon, because it adopts an sp hybridization, has 1, 2 half-filled p orbitals and 1, 2 available sp hybrid orbitals. Nitrogen, if it's sp hybridized, has the same 2 sp hybrid orbitals and 2 half-filled p orbitals. One thing I'd like you to note is because nitrogen has 5 electrons, one of its sp orbitals is used to hold a lone pair. Now, let's put this together and map this onto our Lewis structure. So carbon here and nitrogen have a sigma bond. So thinking about the carbon-nitrogen here, we have our available hybrid orbital. We can overlap these sp hybrid orbitals to make our sigma bond. So let's draw that here. So this sigma bond is formed via the overlap between the carbon sp and nitrogen sp orbitals. By the same token, we can form 2 pi bonds via overlapping the carbon and nitrogen p orbitals. We're not going to worry about their relative energies for now, just the fact that we have 2 half-filled p orbitals that we can overlap. Let's draw these using some different colors now. So carbon and nitrogen both have a half-filled p orbital that we can overlap to form a pi bond between the carbon 2p and nitrogen 2p orbitals. Our last pi bond is also perpendicular to the bond axis. One thing I'd like you to note, and one thing that I discussed briefly, is that the p orbitals are arranged along different axes, right? So when you have these 2 leftover half-filled p orbitals, these 2 leftover half-filled p orbitals that we use to form our pi bonds, they're going to be perpendicular to one another. Just an important little subtlety that I want to draw your attention to. Just like before, we have 2 half-filled p orbitals that we can overlap to form a pi bond. Wonderful. Now, it's important to note the nitrogen lone pair is held in an sp hybrid orbital. Finally, the carbon-hydrogen bond, which is a sigma bond, is formed via the overlap of the carbon sp and the hydrogen 1s orbital. So this sigma bond, let me draw this up here. Perfect. So with this, we've generated a full orbital diagram, noting each of our bonding orbitals and what orbitals we have overlapped to form each bond. These diagrams are extremely helpful for understanding bond length, strength, and reactivity. So again, just in terms of general process, you draw a Lewis structure, you identify the hybridization of each atom, you draw out your post-hybridization orbital box diagram, and then you note and determine what orbitals are we overlapping to form each bond. A lot of this resolves itself very quickly once you identify the hybridization of each of your central atoms. Let's take a look at another example. In this case, we're asked to draw an orbital diagram for CH2NH2. Pretty interesting compound. So, I'd like you to take a moment, pause this video, work out on drawing an orbital diagram, and we'll discuss this example momentarily. Okay, so first and foremost, let's get a Lewis structure going. So in terms of valence electrons, carbon contributes 4 valence electrons, hydrogen contributes 1, but we have 4 hydrogen atoms, and nitrogen contributes 5 electrons, CH2, NH2 plus. Well, we can do either. Let's look at the cationic form, as that's probably most likely what we're going to see. We're going to subtract 1 electron from our total to account for the +1 charge. So in this case, we have 12 electrons remaining. Let's take a few moments now, and I'll give you a few more seconds and minutes to work through this example. You may want to pause the video at this time. I'd like you to draw out a complete Lewis structure for this compound, and then I'd like you to complete the orbital box diagram and write out a full orbital diagram for this compound. Okay, so first, in terms of completing the Lewis structure, carbon and nitrogen are going to be the central atoms in this case. In this case, we'll surround each carbon and nitrogen atom with 2 hydrogens each. From here, we'll form 1 bond each. 2, 4, 6, 8, 10. That uses up 10 electrons. We have 2 electrons remaining. We're going to place our last 2 electrons on nitrogen. From here, to fulfill the octet, we're going to replace our lone pair with a double bond between carbon and nitrogen. Okay, from here now, we can identify the hybridization of each atom. So in this case, this nitrogen has 3 bonded atoms. It has 3 sigma bonds and 1 pi bond. And the same is true for carbon. 3 bonded atoms tells us that both nitrogen and carbon have an sp2 hybridization. And from here, this gives us all the information we need to construct a reasonable orbital box diagram. For carbon, this is what carbon's going to look like. 1, 2, 3, 4. 1, 2, 3. In this case, because it's sp2, we have 3 sp2 hybrid orbitals and 1 half-filled p orbital. For nitrogen, because it has this +1 formal charge, which we can see from the fact 5 minus 4 gives us +1, this nitrogen again is sp2 hybridized. So we have 3 sp2 hybrid orbitals and a p orbital. Except this time, rather than having a lone pair, the nitrogen, because it's nitrogen plus, has 1 less electron than usual, and as such, it can use all 3 of its sp2 orbitals for bonding. Now, once we have these orbital box diagrams established, also noting that hydrogen has a 1s orbital that's half filled, let's begin to describe what orbitals are used to form each of the sigma and pi bonds. And even if you weren't able to identify that for nitrogen plus it has 1 less electron, as long as you get the hybridization of each of your atoms, you're good to go in terms of constructing a orbital diagram. So first, the carbon-nitrogen single bond, the sigma bond, is formed via the overlap of our hybrid orbitals. So this is a sigma bond formed between a carbon sp2 hybrid orbital and the nitrogen sp2 hybrid orbital. So the first single bond between carbon and nitrogen is formed via the overlap of our hybrid orbitals. By the same token, the nitrogen-hydrogen single bonds are formed via the overlap of the nitrogen sp2 and hydrogen 1s orbitals. Likewise, the carbon-hydrogen bond is formed via the overlap as a sigma bond between the carbon sp2 and hydrogen 1s orbitals. So as long as you identify the hybridization, you can identify what orbital each atom is using to form each bond. Finally, this pi bond here, pi bonds are formed via the overlap of half-filled p orbitals. So the pi bond in this case is formed via the overlap of the carbon 2p and nitrogen 2p orbitals. So once you identify the hybridization of each atom, you can in turn draw out an orbital diagram because you know what orbital, specifically what hybrid orbital, is being used to form the sigma bonds, and you know that the pi bonds are formed via the overlap of p orbitals. Okay, so we've done two examples discussing two different types of hybridization for our central atoms. Let's now look at another case study here, in which case we are labeling the orbitals used to form a given bond. So I'll do the first example and then you'll do the second. So we're asked to label the orbitals used to form, in this case, bonds labeled number 1 and 2. So let's look at bond number 1 in detail here. This carbon here has 1, 2, 3 bonded atoms. That tells us that this carbon is sp2. The other carbon has 1, 2, 3 bonded atoms, so it's also sp2. You can also tell by the fact that there are 1, 2, 3 sigma bonds and 1 pi bond attached to each of these carbons for bond number 1. So for bond 1, we have a sigma bond, which is the overlap of our hybrid orbitals, so carbon sp2 plus carbon sp2, and then a pi bond, which is formed via the overlap of the carbon 2p orbitals. For bond number 2, in this case, it's just a single bond here. So let's look at this second atom. This carbon has 1, 2, 3, 4 groups, 4 bonded atoms. And as such, this second carbon here is going to be sp3. So for bond number 2, which is just a sigma bond between these two carbons, it involves the overlap of the two hybrid orbitals, the carbon sp3 orbital and the carbon sp2 hybrid orbital. Okay, so as you can see, you can identify what orbitals are used to form a given bond if you identify the hybridization of each atom participating in that bond, with the obvious caveat being that pi bonds are formed via the overlap of p orbitals. So I'd like you now to turn your attention to this second example. I'd like you to pause the video at this time and work through the second example, and we'll discuss this second example momentarily. Okay, so first let's identify hybridization. This carbon here has 1, 2 bonded atoms, so it has an sp hybridization. This carbon here has 1, 2, 3 bonded atoms, so it's sp2. Oxygen, yes, it has a bonded atom in 2 lone pairs. In this case, oxygen doesn't necessarily have to hybridize because, as we've seen previously, it can accommodate forming two bonds using just its available p orbitals. So, looking at bond number 1 between oxygen and carbon, there are two components to this bond between carbon and oxygen. The sigma bond, which is the overlap of the carbon hybrid orbital and the oxygen 2p orbital, and the pi bond, which is the overlap between the carbon 2p and oxygen 2p orbital. Looking at bond number 2, that's just a single bond, which is the overlap of our hybrid orbitals. So we have a carbon sp3 and a carbon sp orbital overlapping to make this sigma bond. So why is this important again? Because if you can identify hybridization, you have some information on the bond length, bond strength, and bond energy. These orbital diagrams are really critical to be able to draw and interpret. Okay, we're now going to talk about VSEPR theory. So VSEPR theory focuses on understanding molecular shape and geometry. So what is VSEPR theory? VSEPR theory relies on this idea that bonds are electron pairs. And electron lone pairs and electron pairs in bonds repel each other. As such, electrons in bonds and lone pairs are arranged to minimize electron-electron repulsions. So, for example, part of the reason why nitrogen in ammonia, for example, adopts this tetrahedral-like geometry is in part to have the maximum distance between both the bonded atoms and the electrons found in each bond and the maximum distance between the lone pair and the bonding electrons. In VSEPR theory, the geometry of a molecule depends on the steric number, where the steric number is the total number of electron groups. The steric number can be calculated by taking the number of bonded atoms plus the number of lone pairs. Another definition of an electron group or charged sphere is a single lone pair of electrons or a bonded atom. Important to note, double triple bonds are counted as one bonded atom or one charged sphere from the perspective of VSEPR theory. One other way to think about it, to tie this back to our prior discussions of hybridization, when you're looking at steric number, you're really focusing on the number of sigma bonds attached to a given atom. So let's take a look at some geometries. The linear geometry has two charged spheres, a steric number of 2, and the bond angle is 180 degrees. You will often see the linear geometry in cases where your central atom is sp hybridized. For example, carbon dioxide. As you can see for carbon dioxide, there are 1, 2 bonded atoms and also 2 sigma bonds attached to our central carbon. This carbon is sp hybridized, and to maximize the distance between these bonding electrons, if we have a circle, which is 360 degrees, and we want to get the maximum distance between 2 points on the circle, we just divide by 2, and this gives us a bond angle of 180 degrees. That's the maximum separation between our bonding electrons. Let's take a look at some trigonal planar geometries, and let's note the impact of a lone pair on the bond angle. So the trigonal planar geometry corresponds to 3 charged spheres, or a steric number of 3. For example, in BF3, as you can see, we have 1, 2, 3 bonded atoms attached to the central atom. Another way to think about it is that boron is forming 3 sigma bonds. Thus, this central boron atom has a hybridization of sp2 and a trigonal planar geometry. This gives us a predicted bond angle of 120 degrees. Why 120? Well, if we take our same circle and divide it by 3 this time, this gives us 120 degrees as the maximum separation between our bonds. Now, what happens if you add a lone pair, such as, for example, in the NO2 minus anion? Now, this lone pair takes up a ton of space, and lone pairs will distort the bond angles and push the bonding electrons away from the lone pair. So instead of a broader 120-degree bond angle, in the bent trigonal planar geometry, we have a reduced 116-degree bond angle. So the bent trigonal planar geometry occurs when we have 3 charged spheres, but there's a lone pair present. This leads to a reduced bond angle of 116 degrees. This nitrogen is still sp2. The reason why the bond angle is distorted is just because we have this lone pair taking up a ton of space. Okay, let's now talk a little bit about the tetrahedral geometries. Probably one of the more important sets of geometries, considering carbon often adopts a tetrahedral geometry, and nitrogen and oxygen are extremely common in organic structures. The tetrahedral geometries are defined by 4 charged spheres having a steric number of 4. At this point, to get the maximum separation between our bonds, it becomes optimal to arrange atoms and electron pairs in 3-dimensional space. Tetrahedral atoms have 3D shape, and this will be very important for later. Now, the common tetrahedral geometry has a steric number of 4 with 0 lone pairs. This gives us a 109.5-degree bond angle. One thing I'd like you to note is, just in this case for methane, CH4, the carbon has 4 bonded atoms. In other words, there are 4 sigma bonds attached to it. And this carbon has an sp3 hybridization. Now, when you start adding lone pairs, the bond angle gets reduced. In the trigonal planar geometry, we have a steric number of 4, but we have a lone pair. This leads to a reduced and distorted 107.5-degree bond angle. So you don't just have to consider the steric number and the hybridization, you also have to pay attention to the number of lone pairs because they distort the bond angle. The bent geometry, such as that found in water, occurs when we have a steric number of 4 and 2 lone pairs. This gives us a distorted 104.5-degree bond angle. Now that we've seen all of these different electron pair and molecular geometries, let's practice what we've learned with some case studies. I'll do the first example and you'll do the second. In this case, we're asked to draw the Lewis structure for CH3OH, methanol, and indicate the bond angles. We're also asked what's the molecular geometry of carbon and oxygen. So let's generate a Lewis structure. I'm going to preview now a fast method of drawing Lewis structures by interpreting this condensed formula. Reading the formula, we have a CH3 group and an OH group connected reading left to right. The oxygen, to get a complete octet and to match the formal charges noted in the formula, has 2 lone pairs. You're welcome to also draw out the Lewis structure using the long form method that we've been using throughout this lecture. I just want us to focus on the key point of this problem, which is identifying molecular geometry of each atom. So, looking at carbon, we have 4 bonded atoms, and we have 0 lone pairs. Thus, this carbon is sp3, and we have a tetrahedral geometry. This tells us that our bond angle in this case around our central carbon atom are 109.5 degrees. As a slightly different example, looking at oxygen, we have two bonded atoms plus two lone pairs. So we have a steric number equal to 2 plus 2 equals 4, but we have two lone pairs. So in this case, even though this oxygen is sp3, instead of being tetrahedral, we have a bent molecular geometry. This in turn gives us a bond angle of 104.5 degrees around the central oxygen atom. Okay, we're now going to look at another example. This time we're looking at CH2N2, and we're asked to identify the molecular geometry of carbon and of the nitrogen atoms. So, this is a pretty interesting class of compound. These are known as azides. So I'd like you to take a few moments to pause the video, work on drawing a Lewis structure for this compound, and then indicating the bond angles. So first and foremost, for CH2N2, let's do the traditional Lewis structure method. So counting out valence electrons, carbon has 4, nitrogen has 5 valence electrons, and we have 2 nitrogen atoms. Hydrogen has 1, but we have 2 hydrogen atoms, giving us 2 valence electrons in total. So we have 16 electrons to work with. We're going to designate the carbon and nitrogens as our central atoms and surround the carbon with the 2 hydrogen atoms. We're then going to form one bond each, 2, 4, 6, 8, giving us 8 electrons remaining. We're then going to place lone pairs on the outermost atoms, in this case our nitrogen atom. So that burns through 6 electrons. We have 2 electrons remaining. And then we're going to place the second lone pair. You can do it on either nitrogen or carbon. We're going to place it on carbon in this case, just because it makes the next few steps occur a little bit more efficiently. But both would work, just to be clear. From here, to fulfill the octet on the central nitrogen, we're going to convert one of our lone pairs into a double bond. This nitrogen in the center still has an incomplete octet, so we're going to form another double bond. As you can see now, looking at this carbon atom has 1, 2, 3 bonded atoms, so a steric number of 3. So it has an sp2 hybridization with 0 lone pairs. Thus, for this carbon, it would be trigonal planar. This central nitrogen has a steric number of 2. It has 2 bonded atoms and 0 lone pairs. And as such, for the nitrogen atom, it would adopt a linear geometry. Of note, this nitrogen is sp hybridized. Importantly, you only need to note the molecular geometry and the bond angles if your central atom is attached to at least 2 other atoms. This nitrogen is just attached at the end of our molecule. There's no bond angle to be had because it's only attached to one other atom. The bond angle around the central carbon will be 120 degrees, and the bond angle around the central nitrogen would be 180 degrees. So we're beginning to see how we can draw a Lewis structure and then get a sense of the bond length, strength, bond angle, and our overall molecular geometry. So we're beginning to be able to interpret and read structures beyond just as flat drawings, but with some three-dimensional character. Okay, so one thing that we have to consider when we look at a given bond is the distribution of electron density in that bond. And to do that, we're going to need to look at electronegativity and its impact on bond polarity. Electronegativity is a measure of how readily an atom of an element attracts electron density in a chemical bond. Electronegativity increases as you move up on the periodic table and to the right on the periodic table. So if we think about electronegativity trends, abbreviated as EN for electronegativity, you can just draw an arrow up and to the right. In terms of a hierarchy of common elements, I've generated the following electronegativity hierarchy. There are a few things that are pretty interesting. First, carbon and hydrogen are pretty much equivalent in terms of electronegativity. And I'd like you to note that carbon is more electronegative than elements such as phosphorus, boron, and silicon. We'll see the importance of that later on. Now, why do we care about electronegativity? Well, the difference in electronegativity between atoms in a bond determines whether a bond is ionic, polar covalent, or pure covalent. If the difference in electronegativity is less than 0.4, you have a pure covalent or nonpolar covalent bond, which entails an equal sharing of electrons. Examples of this include the chlorine-chlorine bond, where you can think of the electron density being equally shared between the two chlorine atoms. Likewise, for a carbon-hydrogen bond, there's a pretty equal sharing of electrons. When the difference of electronegativity starts to get greater than 0.4 and less than 2, you end up with a polar covalent bond, which is an unequal sharing of electrons. So if we think about the carbon-oxygen bond, oxygen is far more electronegative than carbon. And as such, most of the electron density is going to be allocated and surrounding the more electronegative oxygen atom. More of that bonding electron density is going to be held around oxygen. What that means is that oxygen has more electron density. And as such, because electrons have a negative charge, oxygen builds up a partial negative charge. As a consequence as well, carbon has less electron density, and thus it builds up a partial positive charge. We can say that this bond is a polarized or polar bond. One thing to note here, we're still sharing electrons. And this is important as a lead into the next case, where if the difference in electronegativity gets above 2, you start to cross into the realm of an ionic bond, where there's really a transfer of electrons to give a cation and anion. Examples of this are alkyl lithium and organometallic compounds. When you see the formula CH3 lithium, the carbon lithium bond is not a covalent bond. It's really, you have CH3 minus anion and lithium plus. There are no bonding electrons shared between two atoms. Instead, we have an ionic compound where there's a cation and an anion. This is an ionic bond, not covalent. Very important. So, to this end, we have an exercise where we're going to identify the following bonds as polar, nonpolar, or ionic. So in this case, we have a set of 3 bonds. So let's take a look at those examples. So I'd like you to pause the video at this time, work through these examples, and then we'll discuss momentarily. So first and foremost, let's look at the bromine-bromine bond. These are 2 bonds between the same atom. The difference in electronegativity is 0. So this is a nonpolar covalent bond. What's really important is it's not the electronegativity of the atom in a given bond, it's the difference in electronegativity. Looking at the carbon-bromine bond, the difference in electronegativity is going to be greater than zero point 0.4, but not to the point where we're dealing with an ionic compound. So we have a polar covalent bond. Finally, looking at sodium oxide, the difference in electronegativity is greater than 2. This, we have a metal and a non-metal. This is an ionic bond. So we have sodium plus and O2 minus. If we were writing like a full descriptive formula, if we had a compound containing sodium and oxygen, the formula would be Na2O, just for the record. But we're just looking at if we tried to form a bond between sodium and oxygen, this bond would very much be an ionic bond. Okay, so we've talked a lot about bond dipoles, identifying whether a bond is polar or nonpolar. Let's talk about how we can use bond dipoles to get a sense of molecular polarity. So as we've seen, atoms with different electronegativity values will share electrons unequally. Bond dipoles indicate with delta notation that a partial charge has formed. The arrow points towards the more electronegative atom with the partial negative charge and away from the least electronegative atom with the partial positive charge. So for HF, hydrofluoric acid, the hydrogen-fluorine bond, fluorine is miles more electronegative, and as such, we're going to build up a partial negative charge, build up electron density around fluorine, while hydrogen will build up a partial positive charge. So the HF bond is polarized, and the bond dipole points towards the more electronegative fluorine atom. So to apply what we've learned, I'm going to do the first two examples. You'll do the last three. So looking at the carbon-oxygen bond, oxygen is far more electronegative, and as such, our bond dipole arrow will point towards oxygen. For the carbon-phosphorus bond, carbon is actually more electronegative than phosphorus, and as such, the bond dipole will point towards carbon. This is a pretty important thing to note for later on, as we'll see a certain class of reagents known as Wittig reagents that often exploit the fact that the carbon-phosphorus bond is polarized towards carbon. Now that you've seen these first two examples, I'd like you to take a moment, pause the video, and work through these next three examples, which we'll discuss momentarily. Okay, so looking at the carbon-nitrogen bond, nitrogen is by far more electronegative. Looking at the sulfur-oxygen bond, our bond dipole will point towards, in this case, if we compare sulfur and oxygen, oxygen is higher up on the periodic table, it's more electronegative, so we'll draw our bond dipole pointing towards oxygen. Comparing oxygen and nitrogen, oxygen is farther to the right on the periodic table, so the bond dipole will point towards oxygen. Now, we've identified how to draw bond dipoles. Let's talk about molecular polarity. And for that, molecular polarity is the net polarity of a given molecule. Bond dipoles can be treated as vectors centered along the bond between two atoms. Adding the bond dipoles gives the net molecular dipole. I'm going to teach you this method. If you've taken physics, this method is going to be quite familiar. It's known as the head-to-tail method, where you draw the first bond dipole vector, then you draw the second bond dipole vector, except this time you're going to draw the second bond dipole vector from the head of the first vector. Once you've connected your two vector arrows, you're going to draw the final vector from the tail of vector 1 to the head of vector 2. This is the net molecular dipole. This is known as vector addition, and although it sounds somewhat complicated, it's quite simple in practice. So let's take a look at dichloromethane. I'm going to draw out the Lewis structure for dichloromethane. As you can see, this central carbon atom has 4 bonded atoms, so this is tetrahedral. And as such, I'm going to make sure that these bond angles are about 109.5 degrees. Okay, now that we have that established, let's draw this molecule in a way that's a little easier to apply the head to tail method, just so it can be very easy for us to see. Okay, so first and foremost, let's now draw out our 2 bond dipoles. So here's our first bond dipole, here's the second bond dipole. Now, if I want to get my net molecular dipole, I take my first dipole arrow and then I draw the second dipole arrow from the head of the first. So see how I connected my 2 dipole arrows? Now, if I want the net dipole, I just draw an arrow from the tail of the first to the head of the last. So this is our net dipole. So what this is telling us is that overall, our net molecular dipole, the molecule does have a net molecular dipole, and it's pointing in between the 2 carbon chlorine bonds. Electron density is being pulled towards our chlorine atoms. And overall, there's more electron density on the side of our molecule containing the chlorine atoms. So I'd like you now to try this second example with formaldehyde. You'll want to draw the Lewis structure, draw your bond dipoles, and then estimate your molecular dipole. Note, I didn't care too much about the carbon-hydrogen bonds because those bonds are functionally nonpolar. So I'd like you to pause the video at this time, work through this second example, and then we'll discuss momentarily. So looking at formaldehyde in this case, drawing the Lewis structure for formaldehyde, you'll end up with a structure that looks like this. Now, this one is pretty straightforward here. There's really only one bond that's polarized, which is the carbon-oxygen bond. And so the bond dipole is going to match very much closely with the molecular dipole. Now, am I expecting you to calculate a perfect net molecular dipole? No, but you should be able to estimate whether a molecule is net polar or nonpolar and the approximate direction of its net dipole. Okay, so let's talk about molecular polarity and geometry. Specifically, this idea of polar versus nonpolar molecules. So a molecule can only be polar if it has polar bonds, and those polar bonds give a net dipole. Symmetrical arrangements of polar bonds with the same electronegativity difference will actually yield a net nonpolar molecule. We'll see an example of this. So to this end, I've created some criteria you can use to test whether a molecule is polar or nonpolar. A molecule is nonpolar, not polar, if all atoms bonded to the central atom are identical, or if the only bonds are carbon-hydrogen bonds. Or, in addition, the central atom has no lone pairs and it has a symmetrical geometry, be it linear, trigonal planar, tetrahedral, or square planar. If both of these criteria are met, then your molecule is nonpolar. Otherwise, the molecule is polar. So let's look at an example of this phenomena, CO2, which looks something like this. Carbon dioxide, it does have polar bonds. There are bond dipoles, but the bond dipoles are arranged symmetrically. So the bond dipoles cancel. Looking at our test, the central carbon is bonded to the same atom, oxygen, and the central atom has no lone pairs and a symmetrical linear geometry. So CO2 we would consider non-polar. Let's apply what we've learned here and let's look at some case studies. So in this case, we're asked to draw the Lewis structure for the following compound and determine whether the molecule is polar and draw a molecular dipole. So first, I'm going to draw the Lewis structure for this compound. I'll be doing this first example and you'll work on the second. From here, let's identify the bond dipoles. So we have these two bond dipoles. Using the head to tail method that I've discussed earlier, I'm going to draw my two bond dipoles, the first one and then the second one starting from the head of the first. I'm going to draw from the tail of the first arrow to the head of the second, and this gives us our net dipole. So this tells us our net molecular dipole is pointing up towards sulfur. Now, because we have a net molecular dipole, we would consider this molecule polar. There are two reasons for this. One, we have polar bonds, and two, we have a non-symmetrical geometry. It's bent. How do we know this geometry is not symmetrical? The bent geometry has a lone pair. This distorts our bond angles. Our bond dipoles are not symmetrically arranged. They're pointing in a given direction, and they add together to give a net bond dipole. Now, with this example established, and the fact that we identified this molecule as polar, I'd like you to try this second example. So please pause the video at this time, and then I'd like you to work through the following example, which we'll discuss momentarily. Okay, so first we need a Lewis structure. Carbon tetrachloride looks something like this. Used to be used as a pretty common organic solvent, not used so much anymore due to its pretty high toxicity and long-term negative health effects. So here's Lewis structure for carbon tetrachloride. Looking at the central carbon, we see we have 4 bonded atoms, so this central carbon is tetrahedral. This should immediately set off a minor alarm bell in that this tetrahedral geometry is symmetrical. As you can see, carbon is bonded to the same atom, so we have the same bond dipole. Because we have this carbon that is one having the same bond dipole for each bond, we have just the same carbon-chlorine bond 4 times, and we have a symmetrical geometry. Looking at our criteria, looking at the test that we generated, a molecule is nonpolar if all atoms bonded to the central atom are identical, and the central atom has no lone pairs and or a symmetrical geometry. Both of these criteria are met. Carbon tetrachloride, then based on this general rule of thumb, would be considered nonpolar.